Today, we're going to pull back the curtain on math itself. We're going on a journey to find the absolute, unshakable foundation that the whole thing is built on, starting with pure logic and going all the way to the very strange nature of infinity. It all kicks off with a question that sounds really simple, but it's one of the deepest you can ask. Seriously, forget everything you've ever memorized from a textbook. How can we actually prove, with zero doubt, that something is correct?
To even begin to answer that, mathematicians realized they couldn't just take things for granted. They had to build a system from the ground up, a set of rules for making arguments so solid, so airtight, that the conclusions would be completely undeniable. And that system, well, that's the art of the mathematical proof.
But here's the thing. This quest for perfect, unbreakable logic, it hit a massive wall almost right away. It turns out, if you're not incredibly careful, logic itself can get tied in a knot, and, well, everything just breaks.
A famous example of this is Russell's paradox. See, back in the day, the rules for defining what a set is, which is really just a collection of stuff, were pretty loose. But the philosopher Bertrand Russell found a catastrophic flaw in this seemingly simple idea.
Okay, this is a total mind-bender, so stick with me. A great way to think about it is the barber paradox. Imagine a barber who shaves only the men in his village who do not shave themselves. So the big question is, who shaves the barber? If he shaves himself, he violates his own rule, because he's only supposed to shave guys who don't shave themselves. But if he doesn't shave himself, then he fits the description of someone he's supposed to shave. It's an impossible loop, a complete logical meltdown. And that's the exact same problem you see on the screen with that set R. It just breaks everything.
So, this paradox caused a real crisis. Mathematicians knew they had to get serious and create some new rules. The solution was to build a formal toolkit, a set of absolutely airtight strategies for constructing arguments that could never, ever collapse like that. Now, don't think of these as boring textbook rules. Think of them as detective strategies for uncovering the truth. You've got your direct proof. That's the straight shot. If A is true, then B must be true. Simple. Then there's contraposition, which is kind of like looking at the problem in a mirror. And my absolute favorite, proof by contradiction. This one is like setting a clever trap.
So let's see that clever trap in action. I mean, how on earth would you prove that the square root of 2 can never be written as a simple fraction? You can't just check every fraction in existence, that's impossible. But with proof by contradiction, it becomes downright elegant.
So first, we lay the trap. We're going to assume the exact opposite of what we're trying to prove. Let's just pretend for a minute that the square root of 2 is a fraction, p divided by q. And a key part of this is assuming we've already simplified it as much as possible. Like you wouldn't write 2/4, you'd write 1/2. Okay, now for some simple algebra. If we just square both sides of that equation and move things around a bit, we get a new statement. P squared equals 2 times q squared. Still with me? Nothing tricky has happened yet.
And right here, this is our first big clue. That equation tells us that p squared has to be an even number, right? Because it's 2 times something. Well, think about it. An odd number times an odd number is always odd. So for a number squared to be even, the number itself must be even. So we've just proved p is an even number.
Go wait, here comes the plot twist. Since we know p is even, we can describe it as 2 times some other whole number. Let's call it k. Now if we plug 2k back into our equation where p was, we get 2k squared equals 2q squared. That simplifies to 4k squared equals 2q squared. Divide both sides by 2, and what do you get? 2k squared equals q squared. Whoa, look at that. Now we've just shown that q squared has to be even, which means q itself must also be even. And snap, the trap springs shut. Remember how we started? We assumed our fraction p over q was simplified all the way down. But we just used flawless logic to prove that both p and q have to be even numbers, which means the fraction could be simplified by dividing by 2. That is a flat-out contradiction. It's impossible. So our very first assumption must have been totally wrong. The square root of 2 simply cannot be a fraction.
Okay, so with these powerful, reliable proof techniques, mathematicians could finally start building. But what do you build with when you're starting from absolute zero? Well, they decided to build the entire universe of numbers from, and I mean this literally, nothing.
The most basic building block, the primordial atom of this new mathematical universe, is the idea of a set. It's just a collection of things. And the simplest set of all? The empty set. The set that contains absolutely nothing. And from this void, we can construct everything. This is where it gets wild. The number 0 is defined as that empty set. The number 1 is defined as the set that contains the empty set. The number 2 is the set containing those first two ideas. It just keeps building. And this lets us define even tricky things like negative numbers. The integer -3 isn't just a minus sign next to a 3. It's formally defined as the idea of a difference, represented by a whole class of pairs like 0, 3, 1, 4, and so on. We're building abstract concepts out of rock-solid logic.
Now that we've built our numbers, we can take these same tools, sets, and logic, and aim them at one of the most famously mind-bending concepts of all, infinity. And let me tell you, this is where our everyday intuition just goes right out the window. Let me ask you a question. Which of these two groups of numbers is bigger? You've got the natural, or counting numbers, 1, 2, 3, and so on forever. Or you have the integers, which is all the negatives, all the positives, and 0. I mean, it seems obvious, right? The integers have to be way bigger. Nope. Turns out they are exactly the same size. How is that even possible? Well, in the logic of sets, two sets are the same size if you can create a perfect one-to-one pairing between them. And as you can see, we can create a list that pairs every single integer with one of the natural numbers, leaving nobody out.
What this shows is that any infinite set that you can, in theory, line up and put into a list is called countably infinite. And what's really amazing is this includes not just the integers, but even the set of all fractions, which seems like it should be way, way bigger. They're all the same size of infinity.
Well, that just begs the question, doesn't it? If all of those different sets are actually the same size of infinity, could there be another level? Is there a bigger kind of infinity, one that's so vast you literally can't put it in a list to be counted? The answer is a huge yes, and the proof for it is one of the most beautiful and clever ideas in all of math. It's called Cantor's diagonal proof. Imagine you made a list that you claimed contained every single possible infinite set of numbers. We can prove you're wrong by creating a new number that's guaranteed not to be on your list. Watch this. We look at the first digit of the first number. It's a 1, so we make the first digit of our new number a 0. Then we look at the second digit of the second number. It's a 1, so we make our second digit a 0. We keep going down the diagonal, just flipping the digit every time. The new number we're building can't be the first one on the list because it differs in the first spot. It can't be the second one because it differs in the second spot. It can't be anywhere on the list. And the conclusion from that is just staggering. No matter what list you make, we can always create a number that's not on it. This means that a complete list is impossible. The set of all possible number sets is a fundamentally bigger, more powerful, uncountable infinity. There isn't just one infinity, there's an infinite ladder of them. And that leaves us with a pretty profound final thought. We started with nothing but the idea of logic. From there, we built numbers, structure, and we discovered that there are different sizes of infinity. It really makes you wonder, what other strange, beautiful realities are just out there waiting in the realm of pure logic for someone to come along and build the proof that brings them to life?